Chapter 14 in class exercise 4, problem number 14.13. The 2 kilogram pendulum blob is released from rest when it's at A. Determine the speed of the bob and the tension in the cord when the bob passes through its lowest position at B. So we can solve this problem using conservation of energy principle. So let's define the datum for potential energy. We have freedom to define the datum anywhere, but I prefer to define the datum at the lower position so that I always get the positive potential energy. So relative to this position, this height is 1.5 meters. It's given here. So we can apply this equation, conservation of energy, and gravity is the only force that's doing the work. So it's we can apply the conservation of energy concept. So TA plus VA is equal to TB plus VB is equal to constant. Okay, where TA is kinetic energy at A, so 1/2 VA square. This V is for potential energy, not for velocity. So it's mgHA is the potential energy because of the height HA from the datum. TB is 1/2 mVB square and it's mgHB. Now we can substitute the numbers here. Blob is initially at rest, so its velocity at A is 0. So this is 0. mgHA is 1.5 meters equal to 1/2 mVB square. So 1/2 m is 1.5 kilograms. 2 kilogram bob, yes, m is 2 kilogram bob, VB square, and HB, height from the datum, height from this line for B is 0 because B is on that line. So this is 0. So what we are left with is 2 times 9.81 times 1.5 is equal to, this 2 will get cancelled, is equal to VB square. So we get VB is equal to 5.42 meters per second. So this is how we apply the conservation of energy concept. Define the datum, measure the height from the datum for different points of interest, record the velocities based on the problem definition, and apply the conservation of energy equation. We also need to determine the tension in the cord when it reaches at B. So that's the different question. So when it reaches at B, it's actually going through this circular motion. So we can apply normal tangent coordinate system at B. So for that, okay, let's define B as this lowest point and define our normal tangent coordinate system. So this is tangent, this is normal. This is W equal to mg, and in this direction tension T in the cord is applied. So this cord has tension T going towards center when it is at B. So this is tension T and the weight X downward, and this is point B. Now we can apply this equation, sum of forces, because tension forces along the normal direction. So sum of forces along normal direction is equal to mass times normal acceleration. Going up is positive. That means T is positive because it's in that direction, minus mg is negative, equals mv square vb square divided by radius of curvature, because this is applied at point P. Okay, so T is equal to mg plus m vb square divided by radius of curvature. When we substitute all the numbers here, such as this is 2 kilogram, this is gravity, so it's 9.81, again 2 kilogram, VB is here 5.42 square divided by radius of curvature is 1.5 meters, we get 58.79 newtons. That's the tension force in the cord at B. Okay, so that's solution of problem 1413. Let's work on the next problem, 1469, for same in class exercise 4. Now, the 5 kilogram collar has a velocity of 5 meters per second to the right when it is at A. So at A, it has the velocity VA, 5 meters per second. It then travels along the smooth glide, so there is no friction, or we neglect the friction along this track. Determine its speed when its center reaches point B and the normal force it exerted. So there are two questions. Question number one is here, and this is question number two. Normal force it exerts on the rod at this point. The spring has unstretched length of 100 millimeter. Now, spring constant is in meters, so we would like to make sure that everything is in newtons and meters. So spring length is 100 millimeter, unstretched length, or L0 for the spring. So we can call that L0 as 0.1 meters. 100 divided by 1000. Okay, so that's 0.1 meters. Similar to that, this dimension we will consider that as 0.2 meters, and this distance also is 0.2 meters. Okay, we convert everything into meters, not in millimeters. So what happens is we need to, so there are both spring as well as the gravity are the forces they do work here. So spring is stretched at A and it's a little bit more stretched at B. So spring is doing some work as well as the gravity is also doing some work. So its first step is we define our datum. So let's define our datum at lower point, which is B. So that's our datum. Relative to that, we measure the height for A. So that is HA, and height A is 0.2 meters. Same as this. So this radius is 0.2. So this is 0.2 as well. So 0.2 meters. And then HB is 0. Spring, when it's here, this is the length of the spring. Let's call this LA, which is length of the spring when the block or the collar is at A. And LB is when length of the spring, when the collar is at B. So this is LB all the way. So we need to calculate all these parameters before we apply conservation of energy concept. So let's calculate length of the spring when its collar is at A, which is length of this line here, which is 0.2 plus square plus 0.2 square. It's a triangle here. Okay, so we need to calculate LA. We know this is 0.2, we know this is 0.2, so we can calculate this using Pythagoras. So LA is square root of 0.2 square plus 0.2 square, which is 0.2828 meters. So that means deformation of the spring when the collar is at A, which is SA, equal to LA minus unstretched length of the spring. That is the original length of the spring, LA minus L0, and we can call this 0.1818 meters. Step number two, same LB, which is very easy. It's all the way from here to here. So that is 0.2 plus 0.2, so 0.4 meters. And SB is LB minus original or unstretched length for the spring. And that's 0.4 minus 0.1 is equal to 0.3 meters. So it's time to calculate spring potential energy at A and B. So V spring at A, which is VEA, equals 1/2 KSA square. Now K is given as 50, so it's 1/2 50. SA is this number, 1818 square. Okay, and that is 0.835 joule. At B, 1/2 K SB square. So 1/2 50. This is SB. 0.3 square. 2.25 joule. Potential energy because of gravity, Vg at A is equal to mg at A. That's 5 kilogram multiplied by 9.81 multiplied by 0.2 for HA. So this is 9.81 Vg at B is mghb, which is 0 because hb is 0. B is at the datum. So now it's time to apply the final equation that TA between A and B plus VA is equal to TB plus VB. We can expand this equation conservation as V potential energy at A plus V gravitational energy at A equals TB plus V potential energy at B plus V gravitational energy at B. Remember that this is actually made up of two terms. Okay, so this is made up of two terms. And now it's time to substitute all of these energies here and solve for VB. So when you substitute all the numbers like TA, B, VE at A and B and VG at A and B, based on this calculations here, we get VB is equal to 5.325 meters per second. So this is velocity of block at B. Yeah, please don't confuse between like velocity and potential energy because of gravity. So that's capital V for potential energy, and for velocity we can use like small v. So maybe like use small v here, VV. And now so that's one part of the question. And the second part is what is the normal force it exerts on the rod? So this collar, when it reaches here, how much force it exerts on this rod? So that's what we need to calculate. So for that we apply okay, so this is B and this is the position of the collar. We apply normal tangent coordinate system once again. So this is tangential axis, this is normal axis, and that's point B. And the normal force that it experiences is this normal force plus, because there is spring here, the spring is when stretched, this spring will apply the force on the collar in this direction, F spring. So there is one more force here, F, coming from spring. Okay. And then we can apply the equations. We can calculate this spring force first. F spring force at B is equal to K times SB, which is 50 times 0.3. K is spring constant, is 15 newtons. And then we can apply equations of motion, sum of forces along normal direction, which is this axis, is equal to mass times normal acceleration at B, which is mass times VB square divided by radius of curvature. And the forces are spring as well as normal force, and they both are in the positive n direction, so they are N plus F spring is equal to this. So we can calculate N is equal to M VB square divided by rho minus F spring, where F spring is 15 newtons. And we know mass of the collar, which is 5 kilogram. We know VB, we have just calculated this here, velocity of the block or collar at B, which is 5.325, divided by radius of curvature, which is 0.2. See, radius of curvature is the radius of curvature of this part only, this bend only, and that's 0.2 meters. Minus 15. And the answer is 694 newtons after rounding to three significant figures. By the way, this N stands for normal force, and this N is for newtons. Unit. So that's the end of in-class exercise 4.